I am Bert from the Met Office in Belgium. Together with Veronica and Stefan, we developed within CSTools bias correction or calibration method. Now, why would we use bias correction for seasonal forecast? And this is a very oversimplified picture. What you see here is the global mean temperature. It has a certain trend. But we know that if we initialize our model very close to the observations, then quite quickly, if we run the model, it goes off to another line and it has a different trend. Now, it doesn't mean that the model is useless or has no skill. It means that we have to compensate for that. Another thing is that seasonal forecasting is done using ensemble forecasting to have a probability for certain events to happen. We want such probabilities to be reliable. What do I mean? Now, for instance, for next summer, if the models predict with 70% probability that the summer will be very hot, then for similar forecasts in the past, we want to see that effectively 70% of the cases this happened. Now, in practice, models have this bias, and it depends also on when the model was initialized. You can see, for instance, for the ECMWF system 4, this is the bias for different initialization periods. Now, how is the bias done, the bias correction done in practice? So what we have, we look at the observations and the forecast of the past, and we want to learn, we compare them, and we want to learn how the model was wrong, and then we want to correct that for a future forecast. So typically you have two data sets. One is the training data set and one is the evaluation data set, on which you can also see whether the model was improved or not, the bias correction improved the forecast or not. Now the tool is Calibration, also CST calibration, and it is a member by member bias correction scheme, meaning that if you input a forecast, it gives out corrected. If you input an ensemble forecast, it corrects each of the ensemble members individually. So what does it need? It needs the model input, the observation input, and the more models, forecast and observations you give, the more of course it can learn from the mistakes of the past, and the better will be the correction. There are 4 calibration methods. So the first one and the most simple one is the bias calibration. Then the other one, FMOS, corrects the variability. And then these other two, they also correct the ensemble spread and the reliability. The evaluation method pertains to the distinction between the training dataset and the evaluation datasets. So typically they should be independent, and that is when you have the leave one out option, but they could also be the same, and then you have to use in sample. I will present a small example using the ECMWF System 5 forecast, using all the forecasts from 93 to 2016, issued on May 1st. It has 25 the ensemble forecast has 25 members and a maximum lead time of 8 months. And I will compare this forecast with ERA interim, which I will use as the observation. Now, I used a simple average monthly temperature over Europe, but you might as well use apply the methods, the calibration method, for all the grid points, or use daily values, but I will use monthly temperature anomalies over the whole of Europe. So this is the example that I will show in RStudio. So first I load the CSTools package. Then I will load 2 plotting functions, which I will use later. So plot 1 forecast and also a box plot of all the forecasts. And the code that I have further loads all the ECMWF System 5 data and the observations, but it takes some time. So since I have saved it on a disk, I will simply continue by loading the data. that. I then extract from it the observations here and the model, and make an object that can be read by the CSTools. I calculate the anomaly for each month. It's not strictly necessary. Also, the CST calibration can be applied without the anomaly extraction, but for visualization this is easier. That's why I use it now. So let's look now what is in these two data sets. So this is the forecast. It has 25 members as mentioned before, 24 starting dates, and 8 months of lead time. Whereas the observation has the same, but it has of course only one member. So I will simply plot one example forecast. So what you see here is on the x-axis is the month, and this is the forecast in 93, and you see it starts off quite cold and it continues to be quite cold, and indeed the models also have a temperature anomaly which is below 0, but they are still too warm. What you can see also here is that after 8 months the model spread has gone very wide. So I continue now by running the calibration method. So I use mean squared error min, that also calibrates the ensemble spread, and the leave one out, so that has independent training and evaluation data sets as it's supposed to be. And the output data, again, it's just a simple forecast with 25 members, 24 starting dates, and 8 forecast times or lead times. Now I will show again this plot, the same plot, but a bit squeezed. And then in the background you can see the corrected forecasts, and you can see that the big spread of the ensemble has been diminished here. And in fact, if you visualize all the forecasts, so here are the raw forecasts in blue against the observations, you can see that after month 6 that the spread of the ensemble is too large, whereas it's much larger than the observations. And in the corrected forecast you can see that the spread is the same as the one of the observations.